Buenas tardes. Vamos a empezar la conferencia dentro de este ciclo de Humanidades, que esta vez se celebra, como estáis viendo, en la Escuela Técnica Superior de Ingenieros Industriales, por motivo de la exposición que está en este momento celebrándose, estos días. Está la exposición sobre Nikola Tesla. Voy a hacer brevísimamente el comentario. Nikola Tesla, todos lo conocemos y lo conocéis. Solamente con que hayáis estudiado un poco de física, el campo magnético resulta que se mide en una unidad que es el Tesla. El campo magnético B, no el H, se mide en Tesla, es realmente la inducción magnética que se llama ahora. ¿Por qué se mide en Tesla? Pues porque Tesla es uno de los grandes científicos que desarrollaron muchas de las aplicaciones de la electricidad, muchas de ellas. Por poner un ejemplo, quizá el más ilustrativo, aunque no el más importante, la primera central eléctrica que, aprovechando un salto de agua, sirvió para producir energía eléctrica y dio la iluminación, la energía a la ciudad de Buffalo, en Estados Unidos, pues aprovechó nada menos que las cataratas del Niagara. Bueno, Tesla fue uno de los impulsores y casi como inventor de motores de corriente alterna, y descubrió que la corriente alterna es mucho más útil porque se puede servir para trasladar energía con un voltaje muy alto, y transformadores que sirven primero para elevar la tensión, después para rebajarla para los lugares de utilización, motores eléctricos y muchísimas más cosas que no me voy a extender. La exposición que tenemos aquí es una exposición fantástica en donde se pueden ver muchísimas de estas cosas y todo lo referente a la vida de este gran científico. Y ahora vamos a tener a un conferenciante muy ilustre que además precisamente es especialista en todas estas cosas y que va a ser presentado por Antonio Pérez Yuste, que es profesor titular de esta universidad.
Gracias, Atanasio. Buenas tardes a todos. Bienvenidos a esta conferencia que forma parte del ciclo de conferencias de Humanidades, Arquitectura e Ingeniería de la Universidad Politécnica de Madrid, y forma parte también de la exposición que, con motivo de Nikola Tesla y siendo además la exposición que se utilizó para conmemorar el 150 aniversario del nacimiento de Nikola Tesla en París, tenemos la ocasión de disfrutarla por primera vez en España en el vestíbulo de entrada de esta escuela. La conferencia, como digo, vendrá acompañada de otras dos más que forman parte del ciclo dedicado a Nikola Tesla, que se impartirán próximamente, según está recogido en el programa que les habrán entregado acerca de la exposición, y que darán una visión completa y general de lo que fue la vida y la obra de este significado inventor, al que, como bien ha dicho Atanasio, se le conoce en todo el mundo sobradamente, no solamente por sus contribuciones que las hizo en el campo de la electricidad, en el campo de los sistemas eléctricos de potencia, sino también en otros campos más separados y quizá menos conocidos, como fue la física de partículas, los rayos X, el electromagnetismo y algunas otras iniciativas e ideas más llamativas para su época, como pudieron ser su así llamado por él rayo asesino, o también un sistema de despegue vertical que anticipaba lo que luego ya fue un hecho con el advenimiento de los aviones Harrier. Voy a presentarles al conferenciante que me acompaña. Él es Brian Bowers. Me van a permitir además que le presente en inglés, en deferencia a él mismo. Aprovecharé también para introducirles el motivo de la conferencia y, por último, agradecerle también al doctor Bowers el que haya tenido la amabilidad de asistir y aceptar la invitación para estar aquí hoy con todos nosotros. Entonces, ahora seguiré en inglés. I'm going to switch to English to introduce you and your conference. Dr. Bowers was awarded his doctorate for a thesis on the life and work of Charles Whiston, he has written and lectured in several countries on engineering history, mainly on electrical topics. Until retiring, he was a senior curator in the Science Museum of London and has been chairman of the history group of the Institution of Electrical Engineers, now known as the Institution of Engineering and Technology. He has participated in many of the history conferences organized by the Institution of Electrical Engineers and also the Institution of Electrical and Electronic Engineers. He currently chairs the planning group for the new Museum of Electrical Technology at Pavia, Italy, and he is also the author of several books on the history of electric light and power. Dr. Bowers is our first speaker in a series of conferences organized with the occasion of the exhibition on Tesla, which is shown, as I have said before in Spanish, at the entrance hall of this school, and which was opened yesterday in the presence of the rector of this university and the Croatian ambassador in Spain. Tesla was at the top of his career in the United States in 1892, when, after becoming a naturalized citizen of this country, he started a tour around Europe, giving lectures in cities such as London, Paris, Budapest, Zagreb, and Belgrade. The talk of Dr. Bowers will be related to the time Tesla spent in London. Dr. Bowers, thank you very much to have accepted our invitation to be here with us, to take part in this series of conferences organized around the figure of Tesla, and thank you to be here today. Please, the floor is yours. Thank you very much.
Thank you for that invitation, and thank you for inviting me to Madrid. You must excuse me if I speak in English, but I hope I can be heard, and I know you have a translator. I hope you've all had a good look at the exhibition outside, or if you haven't, that you will do so. It's good. I hope that the organisers will move it to other places, such as London, before very long. I have been asked to speak about Tesla, and in particular his visit to London. He only went to London once, in 1892. He only stayed 2 weeks, and then he made a short visit to Paris. He came at the invitation of British and French electrical engineers to give a lecture with many demonstrations in each city. He was invited because of work he had done in America, which had been reported in various journals, both in America and copied into journals in Europe the previous year. So the name of Tesla was getting quite well known in Europe. One person who heard Tesla give his lecture in London No, right. Sorry.
Let me help you.
We've gone right down to the end. Tesla never had any trouble with his PowerPoint pictures.
Correct.
Thank you.
The problem of life.
Yes. One reporter who heard Tesla lecturing in London wrote afterwards, "The lecture given by Mr. Tesla will long live in the imagination of every person that heard him, opening as it did to many of them, for the first time, apparently limitless possibilities in the applications and control of electricity. Seldom has there been such a gathering of all the foremost electrical authorities of the day on the tiptoe of expectation. When Tesla came to London, he was 36 years old. So we have several questions. Who was Tesla? What had he done in his first 36 years? What was the state of electrical engineering at the time? What were Tesla's discoveries that got him invited to Europe? What did he say in his lecture and how was it received? And of course, what did he do afterwards in his remaining 50 years? Though most of that remaining 50 years, I must say, is the subject for a future lecture in this series. Tesla is usually remembered as a reclusive and eccentric, perhaps rather odd individual who was fascinated by high voltage, high frequency effects, a man who enjoyed creating massive electrical discharges through the air, a man who dreamed of transmitting electric power by such discharges over long distances. But that was really the older man, Tesla, not the up-and-coming engineer who visited London in 1892. What was he like? Well, there are pictures of him outside, but he was a tall, thin man, quite a bit taller than me, and quite a bit thinner. He was born in 1856 at Smiljan, now in Croatia, but then part of the Austro-Hungarian Empire. When he was 7, the family moved to Gospic, where he excelled at school, especially in mathematics. His father, who was a Serbian, was a clergyman of the Greek Orthodox Church. His mother is remembered as being a very inventive person herself, and she is supposed to have made improvements in looms for weaving and various items of agricultural and rural machinery. There were 2 boys and 3 girls in the family, but the other boy was killed in a horse riding accident when Nikola was quite small. Father wanted Nikola to follow him into the priesthood, but Nikola had other ideas. While he was still at school, he became interested in electricity and began to make electrical experiments. He persuaded his father to let him study electricity at the Graz Polytechnic School in Austria, though he couldn't complete the course there because of political and financial complications to do with the changing military situation in that part of the Austro-Hungarian Empire. Later, he also studied at the University of Prague, though he left there without taking a degree, so he really embarked on his electrical career without formal qualifications. But he wanted electrical work, and in 1881 he obtained work with the new National Telephone Company in Budapest. As an aside here, I point out that this boy, who was born in Croatia and spoke Croatian, obviously, went to Austria to learn and must have spoken German, went to Prague and learnt Czech, then got a job in Budapest and learnt Hungarian. Later on, he was to add French and English to his repertoire. But I think he was a bright lad. While he was at the telephone company in Budapest, he was thinking widely about electrical matters, And in particular, one of the things which interested him was the idea of how to make an electric motor that would run on alternating current. He had ideas but no facilities for making machines in Budapest. So he moved, he went to Paris and got work with the Continental Edison company. This company was planning electricity generating stations and electric lighting systems across Western Europe, France in particular, but the adjoining countries as well. So perhaps this is an appropriate moment to pause and think about the state of electrical engineering at the time, round about 1881. What was going on in the electrical world that had so caught the enthusiasm of the schoolboy and young man? Around about 1880, electricity meant, first of all, the electric telegraph. The main cities of Europe were all linked by telegraphs. People could send messages to people in distant places which were ultimately delivered as telegrams by a messenger boy. With the transatlantic cable, it had just become possible to send messages to America. Expensive, but possible. Most ordinary people never used the telegraph themselves, but they were familiar with the idea of sending messages along wires. Telegraph wires were appearing along the main roads of Europe. In 1881, the English writer Thomas Hardy wrote a novel, a story, in which the whole story depends on the fact that the heroine, the lady in the story, could use the telegraph herself. It's an interesting story for historians to read, because when you read it, you realise that Hardy himself, in writing the book, knew about telegraphs in the sense of he knew that there was apparatus that could send messages from here to there, but he didn't actually understand how it worked. Newspapers were making enormous use of the telegraph system, so news was spread much more rapidly and more fully from place to place than ever before. The telegraph system and the newly invented telephone didn't require much electric power to operate them, so most were battery powered. And a lot of research went into electric batteries. Best known of all batteries at that time is probably this is Tesla at that time, or a little earlier. The best known battery was the Leclanché cell, itself invented in 1881, and the basis of the dry cell that we're all familiar with in torches and small electrical devices throughout most of the 20th century, although those cells are gradually being replaced by others. All these things would have intrigued the young man interested in electricity. A lot of skill and ingenuity went into the design and manufacture of telegraph instruments, so there was always plenty to interest the up-and-coming engineer. One of the instruments which I always feel shows the most ingenuity among telegraph engineers is the paper tape reader. The little machine on the left of the paper, on the left of the picture, takes a paper tape which has holes punched in it representing the Morse code of a message. The diagram on the right shows the works. And the idea of this was that the paper tape could pass through the machine very much faster than an operator could work the Morse key. Why do this? Well, the most expensive part of the telephone system was the wire from Madrid to wherever you wanted to send your message. So it made sense, made economic sense, to send messages as fast as possible. So at each telegraph station, a number of people, usually young ladies, were employed punching the messages onto paper tape. And the tapes were then pulled through these machines quite quickly, so the message was transmitted at several hundred words a minute. At the receiving end, another machine read the signals and printed out the message, which could be read at leisure. Another application of electricity just becoming important was in lighting. At first, electric lighting meant the carbon arc. The brilliant light produced by an electric arc between two pieces of carbon had been demonstrated by Humphrey Davy in the early years of the 19th century. But to become a practical source of light, two things were needed. One was a good electricity supply. Now, you could use batteries to supply arc lights, and they were used in theatres, but for practical lighting, street lighting, large-scale lighting, batteries were far too expensive. What was needed was a good generator. And good generators, usually driven by steam engines, began to be available from about 1870. The other requirement for arc lighting was a way of holding the carbons. In your arc lamp, you have two pieces of carbon, end to end, like so, with the spark between them. But in the heat of the spark, the carbons burn away, so you need some sort of mechanism to feed the carbons closer together, but never touching, to keep the arc going. Many designers made arc lamp mechanisms to do this one. These two are English arc lamps, but there were makers all across Europe making similar ones. Essentially, the idea is there are two rods of carbon, one above the other. The upper one can fall gently under gravity, but it's restrained, slowed down by a brake. And the brake is controlled by electromagnets. The arc lamp on the right has two electromagnets. The one at the top, the coil on the top of the machine, is connected in parallel with the arc, so it monitors the voltage across the arc. The lower coil is in series with the arc, so it monitors the current through the arc. As the carbon burns away, the current falls and the voltage increases. So these magnets sense what is happening electrically, and the carbon is allowed to drop down and keep the gap constant. Thank you. The first arc lamps used in street lighting were actually much simpler than these. The Russian inventor Paul Yablitchkov, who was a telegraph engineer first, went to Paris to study electrical matters and had the idea that instead of putting his two carbons end to end, he would have them in parallel and put a strip of plaster between them. His idea was that as the carbons burnt away, the plaster would also burn away, so you had a constant gap remaining. A little bridge of carbon at the top of the carbons fused when the current was turned on and started the arc. Yablitchkov called these a candle. Well, being in France, he called them a bougie. I'm not sure what the Spanish is for a candle. I won't ask.
Let me think.
Right. And these were used in street lighting, first of all in Paris, and this is the Avenue de l'Opéra in the summer of 1881, all lit with Mr. Yablitchkov's candles. Candile. Thank you. A problem with these, of course, was that the candles had to be replaced every day. Sorry, the microphone wire goes under my feet, but I didn't know that. The candle had to be replaced every day, but that didn't matter because the street lighting company employed men who used to go round turning the gas lamps on and off. So instead of doing that, the men went round and changed the candles. When the English newspapers heard what was going on in Paris, there was a bit of protest. They have these marvellous new lights in Paris. Why haven't we got them in London? And a few months later, in December 1881, Jablitschkov candles were used on the Victoria Embankment in London, alongside the River Thames. You can probably see at the top of the picture Big Ben just visible. It's also interesting to note that in putting these Jablitschkov candles along the road, they only used alternate fittings. There had been a gas lamp in each of those columns, but just one electric light replaced two gas lamps, and it was all much brighter. Arc lights were good for railway stations, for large buildings, markets and places like that, but no good for domestic use. What was wanted was a much smaller light. The idea of the incandescent filament lamp that glowed when a current passed through a thin wire, it was an old idea, but there were many problems. What do you use for the filament? It's got to withstand being made white hot and then cooled, and then made white hot again when you want the light, and cooled again, and it's got to do that many times. And then you have got to enclose it in a glass vessel to keep the air out. But it gets hot, so how do you seal the wires through the glass without the glass cracking? And how do you pump enough air out of the glass bulb, to stop the filament oxidizing? The last problem was solved by the invention of the Sprengel air pump in the mid-1870s, and almost immediately several workers managed to make a satisfactory filament lamp. The most successful were the Englishman Joseph Swan, who made the lamp on the left, and the American Thomas Edison, who made the lamp on the right. These were both made in 1878, but there were other inventors in both countries making similar lamps. Incandescent filament lamps were a feature of the first International Electrical Exhibition in Paris in August 1881. By then, both inventors had refined their lamps considerably. This is a picture of a lamp produced by the Swan Company in 1881, the year of that exhibition. It had rather a long glass stem, as you can see, that went into a holder. The design was quickly improved, and these were lamps that were used in England in the 1880s and 90s and up to the First World War. You see that the lamp is held onto the holder by two little springs which also provide the electrical connections. So here was how to light your house. But unless you were going to install your own steam engine and generator in your house, you weren't going to have electricity and you couldn't have electric light. What was needed, of course, was a central power station with wires going to the houses. The first such central power station, which supplied only a very few houses, was in the small English town of Godalming in southern England in November 1881. Generator was made by Siemens, and the lamps were swans like the ones on the screen now. Early the following year, 1882, Edison opened his first power station, which was in central London. And a few months later, his much better known power station at Pearl Street in New York. People sometimes wonder why Edison made his first power station in London and not in New York. I don't know, but I think the answer probably was he wasn't too sure whether it was going to work or not. So let's try it out in another place, not where our friends and financial backers will see if it's a failure. With filament lamps, it was very important to keep the supply voltage constant. With arc lights, you can vary the voltage and the light stays much the same. But with filament lamps, the brightness varies rapidly if the voltage goes up and down. Constant voltages, of course, are more easily achieved with an alternating current system where you can have transformers. And AC also made it possible to transmit power over greater distances. But the design of generators was the first key point. I mentioned that Gramme, a Belgian engineer working in Paris, was producing generators from about 1870. And this is a typical Gramme generator, and vast numbers of these were made during the 1870s and used for supplying lighting and other applications of electricity. A major discovery was that the Gramme generator was reversible. If you take two Gramme machines, connect them together, drive one from a steam engine, then the other will operate as an electric motor. A lot of people had tried to make electric motors earlier in the century, but no one had succeeded in making anything nearly as good as the Gramme machine used as a motor. When Tesla, who was clearly observing all these goings on in the electrical world, when he looked at a Gramme machine, the thing which struck him was that the currents in the rotor of the machine are alternating, but the currents in the wires connecting the two machines together are direct. The change from alternating current to direct current in the generator, or from direct current to alternating current in the motor, is made by the commutator and brushes, which you see in the middle of the machine on the right, just to the right of the rotor. This is always the most difficult part of the machine to manufacture. It's the part which most often goes wrong. So Tesla thought, clearly, a machine in which the alternating current produced in the generator was carried as alternating current to a motor and used in the motor, it just must be better than a direct current system. I have a couple of pictures of that electrical exhibition in Paris that I mentioned. This is the electric lift of the exhibition, and you see the men in the cage being carried up to the next floor. This was powered by one of Mr. Gramme's motors running as one of Mr. Gramme's generators, running as a motor. And you see the men going up in the lift. Outside the exhibition, you could have a ride on an electric tram, driven again by electric motors. A few years later, in Aberdeen, in Scotland, electric power was demonstrated very visibly. There were electric trams along the road, and you can see that the trams are electric. They have an arm reaching up to an overhead wire, and the street is lit by carbon arc lamps. Power stations were beginning to be built. This was a power station built in London, opened in 1892, the year that Tesla came to London. There is no record that I can find of Tesla visiting any power stations when he was in London, but I feel sure that when he was coming, meeting electrical engineers, talking about electrical things, he must have gone and looked at places like this. But when he was in Paris, Tesla was working for the Continental Edison Company, and the most important person there was Charles Batchelor, who was Edison's agent in Europe. Batchelor told Tesla, "You ought to go to America." Batchelor gave him a letter of introduction to Edison, in which he wrote, and I'm interested to see this same letter is exhibited in the exhibition outside, "Dear Mr. Edison, I know two great men. One is you, the other is this young man, Tesla. Please give him a job." Tesla worked for Edison for a time, but the relationship couldn't last. Edison was firmly convinced that direct current was best. Tesla thought the future lay with alternating current. I think it was fairly inevitable that before long they parted company. Tesla obtained financial backers, people willing to put money into his work, and he set up his own firm for the manufacture of alternating current generators, transformers, and arc lighting equipment. But at this time, most electric power was still provided by direct current. And the problem of making an alternating current motor was being studied by several people. The most important were Tesla, of course, in the United States, and also Galileo Ferraris in Italy. And they both had the idea that if you could produce a rotating magnetic field, then an iron rotor would be pulled round and act as a motor. Tesla, or both of them, it's described induction motors, and Tesla also described a synchronous motor in which the rotor keeps in step with the rotating field. And these rotating field motors proved to be the solution to the problem of using alternating current for factory purposes on a large scale. And in addition, by about 1890, Tesla had devised methods of starting and running induction motors on single-phase current. His designs were said to be so good that they had an efficiency of over 90%. I'm not quite sure that the technology existed to measure the efficiency of electric motor very precisely at that time, but certainly his motors found considerable favour. I'm jumping ahead slightly. This is an electric underground railway in London, just been opened just before Tesla came. Here is a drawing from one of Tesla's American motor patents, a drawing of a motor, a two-phase motor. The generator on the right has two lots of brush gear so that alternating current is produced in two circuits with the phases 90 degrees apart. He had another idea illustrated by this motor, which was actually patented in America in 1891 and also published in some English journals. It's a motor with 4 poles. Just 2 of the poles are connected to the electricity supply. And on those, that's the poles at the top and bottom. And on those poles there is another winding which connects to windings on the other 2 poles, so that by transformer action a current is induced in those other 2 poles. And if you think about it, the current in the other 2 poles will be at 90 degrees phase difference to the current in the first 2. So you have, from your single phase supply, a 2-phase field, and the resultant is a rotating magnetic field. At this point, it seems that Tesla considered that he had finished with induction motors. He had done it. Turned to something else. He did, in fact, bring one of his induction motors with him when he came to London. This motor. I don't think you've got any actual Tesla motors in the exhibition. This motor is in the Science Museum in London. It seems that when Tesla came to London in 1892, he brought this electric motor in his luggage. I suspect he found it rather heavy, well, it is heavy, and he gave it to the Science Museum. But at this time, a new topic was attracting Tesla's attention and the attention of electrical engineers generally. And this was the work of Heinrich Hertz in Karlsruhe in Germany. Hertz was following up the theoretical work of the Scottish physicist James Clerk Maxwell, who had predicted that there must be what we now call electromagnetic waves. Is that term understood? Good, thank you. Maxwell predicted that there must be electromagnetic waves, and Hertz set out to produce such waves and detect them. And Hertz's apparatus, mounted on a table here, a spark gap in the equipment on the right, fed from the induction coil, produces electromagnetic waves which are radiated from those 2 discs at the top. And on the left of the table is a simple loop circuit with a small spark gap. And Tesla found that if he had got all the parameters just right, or if the circuits were tuned to the same frequency, then when he set sparks going in the apparatus on the right, a spark appeared at the spark gap on the left. It was the beginning of radio transmission, electromagnetic wave transmission, whatever you like to call it. For Hertz, it was working towards what we now call radio communication, transmitting information across a distance. Tesla saw something different. He saw that power, electric power, was being transmitted through space from the apparatus on the right to the item on the left. And wouldn't it be good, thought Tesla, if we could transmit lots of electric power through space from here to there without having to have long bits of wire connecting things together. He set out to build an alternator to produce high-frequency currents because Hertz was working at high frequencies. He made a machine which would generate at 5 or 10,000 cycles per second, 5 or 10,000 hertz. This was quite difficult to make a machine like this. It needed, he said, several hundred poles on the rotor. There couldn't be any iron in the armature, because of hysteresis losses, and the heating effect of these would soon melt the equipment. He turned to using tuned coupled circuits with induction coils and spark gaps to produce ever higher frequencies. And he found that when he produced very high frequency currents, and you have a demonstration of this in the exhibition outside, he could produce quite spectacular large sparks. He didn't understand really what was happening. He said, in fact, I don't really understand the physics of this, and this must be an encouragement to other engineers. He didn't really understand the physics of what was happening, but he knew that things were happening, and one of the things he thought was that there might be a practical application of his discoveries in electric lighting. He gave a variety of demonstrations at his laboratory in the States, and this was written up widely and copied in the European journals. And his patent for an electric lamp was also copied in Britain. I don't know who actually invited Tesla to come to London and to come to Paris and repeat his lectures, but he was in correspondence with a number of British engineers. There are letters in the IEE archives written just before his visit, correspondence with Sylvanus Thompson, for instance, who was one of the leading engineers in London. Thompson said he had been reading about Tesla's experiments and he looked forward to meeting him and seeing the experiments himself. He was also in touch with William Preece, who was the chief engineer of the British Post Office, the Post Office Telegraph system. Preece lived in Wimbledon, then a village about 10 miles southwest of London, quite close to where I live now, as it happens. Preece invited Tesla to come and stay at his house while he was in London, and to help Tesla get around, he put a horse and carriage at Tesla's disposal, which was very practical. Tesla arrived in London on the 26th of January 1892. 2 days later, the Institution of Electrical Engineers had a new president, William Ayrton, who was giving his inaugural address. And at the end of his address, he made a special announcement. We are to have the pleasure of receiving a most interesting lecture from Mr. Tesla next Wednesday, February the 3rd. And partly because we anticipate a very large attendance, and partly because Mr. Tesla will require special facilities for his experiments, his lecture will, by the kindness of the managers, be delivered at the Royal Institution. At that time, the Institution of Electrical Engineers didn't possess a building of its own. They normally held meetings at the Institution of Civil Engineers, where the lecture theatre was quite small. At the Royal Institution, where Michael Faraday had worked and lectured earlier in the century, they had a large lecture theatre equipped for all sorts of scientific lectures. Alexander Siemens, who was then in charge of the British Siemens Company, agreed to provide generators and other equipment that Tesla needed for his demonstrations. The managers of the Royal Institution thought that this lecture of Tesla's would be very popular. So they put up a notice in the Royal Institution asking members to stay away on the day that the electrical engineers were having their lecture, and they asked Tesla to repeat his lecture for them the next day. Tesla's lecture to the Institution of Electrical Engineers lasted for 2 hours. 2 hours of lecture. The written lecture is published in the institution's journal. It occupies more than 100 pages, and has about 40,000 words. So I assume that Tesla put in a written paper after his actual lecture. He began by acknowledging clearly that his work was built on the work of other people, especially acknowledged the work of William Crookes on electrical discharges in gases at low pressure. He described in detail the construction of his generators and other apparatus, and then he demonstrated to his audience many of the effects that had been reported from his experiments in America. This drawing is from the report in the Journal of the Institution of Electrical Engineers, and you see an arrangement not quite the same as your Tesla discharge outside. Your demonstration outside has a single column with a spark coming from the top. This drawing shows two columns, two wires, with sparks flying between them, producing a bright light. Another arrangement had two rings, and again sparks flying between them, producing a lot of light. Tesla thought, and he told the electrical engineers, that this might be a basis for a new method of lighting. Here was his circuit, basically induction coils fed from a generator, spark gap in the middle, all designed to produce very high voltage, high frequency sparks. And you see his lamps on the right, which are not really ordinary lamps, but they are glass vessels with just a single electrode in them, and they're only connected up by a single wire. Tesla said that with his high frequency induction circuits, you only need a single wire, and as you see with the demonstration outside, you can get some light with just one connection. The Tesla added, it is better if the other end of your high frequency supply is connected to the walls of the room, and those walls are made of metal. At the end of his lecture, Tesla said, "It has been my chief aim in presenting these results to point out features of novelty, to advance those which I am hopeful will serve as starting points of new departures. It's been my chief desire this evening to entertain you with some novel experiments, and your applause tells me that I have succeeded." And there were formal votes of thanks to Tesla and to the Royal Institution for letting them use the room, and to Mr. Siemens for the apparatus. The next evening, Tesla repeated the lecture for members of the Royal Institution. At least it was described as a repeat lecture. It was a very much shorter lecture. I think it was shorter for two reasons. First of all, he didn't have all the technical description of how he made his generators. And secondly, the Royal Institution has a tradition, which goes back to Michael Faraday, that lectures should never last for more than an hour. Faraday said that most people can't actually pay attention for a whole hour, and nobody can be expected to listen to a lecture for longer than that. And the report in the Royal Institution is much shorter. There are a couple of Tesla's lamps, so-called, which he showed allegedly producing electric light. Well, it was producing a sort of electric light, though we have to admit that it is not the way we light rooms today. He left London after a couple of weeks, though visited quite a number of engineers in London. One in particular was Ambrose Fleming, the inventor of the thermionic diode. Tesla went to see him in his laboratory at University College London. And then Tesla went to Paris, where he stayed at the Hôtel de la Paix and repeated his lecture to a joint meeting of the Société de Physique and the Société Internationale des Électriciens in Paris. Just a single lecture. The French journals report the lecture, and it was clearly the same as the lecture he had given in London, though rivalry between Britain and France is always there, and the French journals don't mention the fact that he had just given the lecture in England, and the English journals don't mention the fact that he was just going to France. They both say this is what Mr. Tesla did in America, and then came here. After Paris, he made a last visit back to Croatia, and in fact his mother died while he was there. He went to Belgrade, where by all accounts he received a tumultuous welcome by the city, the nation, the government, academics, a society of engineers, a new choral society, military music, flowers and flags. Quite a welcome for the boy who had left the country years before, gone to America, made good and come back. And the following day he was received by the king, and then he returned to America. His main objective was always the transmission of power across space. Returning, he built a laboratory at Colorado Springs, and he wanted to develop the idea of transmitting power by means of these electrical discharges. And the big photographs you see in the exhibition outside are taken from his Colorado Springs laboratory, those massive discharges. There is a little, shall we say, dare I say, cheating in those photographs, because the camera was clicked several times and the sparks were not all at the same time, so it built up a much more impressive picture probably, but nevertheless it was quite a dramatic experiment. And Tesla had the idea that the Earth was a conductor, and he thought that somewhere up in the sky there was a conducting layer as well, and perhaps if things were tuned just right, we might send electric power over long distances by these electrical discharges. I'm afraid it never worked on the large scale. Tesla continued to enjoy fame, and pictures like this attracted a lot of interest. I don't think he was actually sitting there while the sparks were flying. I think the picture was taken several times and he moved in after the current was turned off. But there we are. He continued to enjoy fame. He made very little money from his work, became poor, in fact, during the last years of his life. But his name was always a good one in public, and the press were always willing to ask Tesla if they wanted a nice quote about anything technical. In 1914, the American Institution of Electrical Engineers, part of what is now the Institution of Electrical and Electronics Engineers, awarded him the Edison Medal for meritorious achievement in his early original work in polyphase and high voltage, high frequency current. I think the word early in that testimonial is important. The medal was for his early work, which was certainly crucial. And he didn't achieve anything like so much in his later years. In his last years, he became a complete recluse, living alone in a New York hotel, finding companionship in the pigeons that came to his window. And he died in January 1943. It was a sad ending, really, for a remarkable career. A much better memorial is perhaps the bronze statue of Tesla at Niagara. Tesla was involved in the equipment for the power station at Niagara. Oh, I've lost a picture. There was another picture of, don't worry, it was only another picture of the same statue. But I was going to say that there is another copy of that statue at Gospic in Croatia. But I think Tesla would have appreciated himself even more two other memorials. The IEEE now give the Nikola Tesla Award every year for outstanding contributions in the field of electric power. And there is the SI unit of magnetic flux, the Tesla. I think that would have pleased him. And of course, there is the exhibition here, a fitting tribute, I think, to a quite remarkable man who played a major part in creating the electrical world that we know today. Thank you.
Thank you very much, Brian. It was an interesting, very interesting conference. And of course, there is also a volcano, a crater on the moon, also called Tesla crater, in addition to all of these things you have named before. And as Faraday said, this lecture has not lasted more than 1 hour, so I think it's a good recommendation from Faraday.
Faraday was very wise.
Very intelligent man. So now that it's time for you, it's time for your questions. You can address your questions in Spanish, or if in English, or if you prefer in Spanish, to our speaker. So just lift your hand, and we will give you the microphone to ask.
Thank you very much. I have two questions. One should be a very simple one, which is, Tesla, did he marry? Did he have a family?
No.
He was living as a bachelor?
That's right. Simple question, simple answer.
Yeah.
No.
All right. The second one is perhaps more a matter of opinion. But, I mean, judging from your presentation, I could see, I will translate it later in Spanish. I could see that Tesla was practically at the high point of his career when he was in his 30s or early 40s.
Yes.
Now, that was happening, say, a little bit more than 1 century ago. I wanted you, as a man of expertise, I wanted your opinion on how this way of doing this environment is compared with the situation today in the world, in Europe, or at least in a big part of Europe, less in Britain. But it's difficult to imagine nowadays an engineer who, at his 30s or early 40s, can make substantial achievements in the engineering world. Para la audiencia, la pregunta la resumo muy rápidamente. Tesla estaba en el clímax de su carrera pues cuando tenía 30 y tantos años o 40 y muy pocos. Entonces la pregunta es ¿cómo juzgaría el doctor Bowers? ¿Cómo juzgaría esa situación que sucedía hace un siglo con lo que acontece hoy en día, donde se ve que hay dificultades extraordinarias para que jóvenes ingenieros puedan llegar a un nivel alto a esas edades?
No hace falta que traduzcamos porque tenemos traductora. De manera que está bien la pregunta que se haga en inglés. It's good, it's right, the question is in English, but we have a translator, so it's right here. Okay.
I think it is very difficult for anyone, an engineer or other, in their 30s or thereabouts to have world-changing discoveries. How old was Tim Berners-Lee when he did the World Wide Web?
Who? Tim Berners-Lee. I don't know, probably 35, probably.
Right. So we have one other example.
But I don't know exactly how old it was.
I think it is very difficult to make such world-changing inventions and discoveries. You've got to find a new field to work in. Tesla got into alternating current when that was just the thing that was starting. Have you a complete new invention up your sleeve that you would like to bring to the world? I said, do you have an idea for a completely new invention, something as new, novel as alternating current or the World Wide Web? You need an idea like that. Nuclear power? Oh, people have talked about nuclear power for years. Yes.
Early phases, very early phases.
Sorry?
Still is in its birth days. And it's something, nuclear power, the problem is there. The possibilities, everybody will agree that are enormous.
Yes.
The possibilities are extraordinary. However, it's such a difficult field, and there are so many things to be found, to be investigated, and to dig into substantial depth, that there is an impasse situation nowadays, complicated by the attitude of the politicians. And you have asked me a question, and if there's a new field, my answer is there's a new field, certainly. There are more. There are perhaps more, and many more than I cannot imagine now. But there are new fields. And the thing is that the social situation towards engineering in the 21st century is substantially different than the social situation in at the termination of the 19th century.
Well, I hope that this university is training some students who, when they're in their 30s or thereabouts, will come up with one of these world-changing discoveries and be another Tesla.
We hope.
You hope? Yes. Then you will be the man who taught another Tesla.
I would like, but I am not.
But Tesla didn't get a degree, remember?
Yes, Tesla didn't get a degree, really. But well, he was a very intelligent man, I think. So probably he's the kind of man that born once in a century, or so it's very difficult to repeat some work like Tesla did nowadays, because now it's a question of work team. All developments now are made with work teams, not by a single person. Sorry.
Well, I would just like to comment that there is a new field also discovered by a so-called new Tesla, who is also Croatian, Marin Soljačić. He works at the MIT, and he discovered the wireless transmission of electric power at short distances. So they call him New Tesla because he's about to try the experiments with longer distances and really put into practice the Tesla's imagination and inventions.
I look forward to seeing that and reading about it in practice.
Aren't there more questions?
Making it run around.
It's a big hall.
Yes.
For one people, for one
Well,
person.
one microphone.
Yes, for one microphone.
Hi, thank you for your speech. This is a short question. Did Tesla know to speak French? Thank you.
I think he must have spoken French because he worked in France for a couple of years, and the accounts in the French journals, I think it is Tesla's words. It isn't a report by somebody else. So I think probably Tesla wrote it in French.
I have read that Tesla was able to speak 7 languages in some book. I don't remember now exactly which book was this one, but I'm trying to remember now that he spoke Croatian, English, French, German,
Hungarian.
Probably Hungarian, probably.
In Budapest for a while.
But he Latin too.
Yes, Latin.
Latin
Yes.
too. He spoke Latin, and I don't remember the 7th language, the 7th one. Czech, probably. But I don't remember exactly. But I'm sure that I read that he spoke 7 languages.
Yes, I have read that statement. He was clearly very good at languages and must have picked them up quite easily when he moved to a country.
Mm-hmm. No more questions, please. En español también, no hay problema, ¿eh? Si es por el idioma, se cambia. Tenemos la capacidad.
Gracias. Una pregunta yo tenía que hacer. ¿Cuándo se decidió dar su nombre para una unidad del campo magnético?
I don't know.
I know.
But
I know. In 1960, in a meeting in Paris in 1960.
1916?
1960.
1960.
1960, okay.
Thank you. Yes, I didn't know what year that was done. I have written that down. Thank you.
Sorry, my last question. I don't want to monopolize that. How did it end up, the relationship between Edison and Tesla? What happened eventually?
Well, they never got on. They never said nice things about each other. They just went separate ways. America is a big country, so they didn't have to meet up together. They just went separately.
There is a tale about the moment when Tesla broke with Edison. Edison put the challenge to Tesla to improve the capacity to generate electricity, and Tesla catch this challenge, and afterwards, after some time, some months, he worked very hardly to develop a better way to generate electricity, And after some months, he came with the way to improve this, to improve the generation of energy, of electricity, by using alternating current instead of direct current. So Edison told to Tesla that if he was able to get it, then he paid $50,000. So when Tesla came with the solution, he claimed for his $50,000, and Edison told Mr. Tesla, you don't know about the American humor. So this tale says that after the answer, Tesla thought to make his own way alone, far from Edison.
Yes, there are many stories about Tesla
stories.
and about Edison, including that one, of course. And it is very difficult to know what is true,
really difficult,
and what isn't. I'm sure there was never a written contract saying I will pay you $50,000.
Sure.
But it was a story that Tesla told to show how nasty a man Edison was to work for, I suppose.
There were more questions there. Over there.
Oh, actually, you have said that Tesla did not finish any technical career. So how can we consider him, or how does he feel as an engineer, physicist, or what?
So what do you call him? Yes. So would Tesla call himself an engineer or a physicist? I think he would have said, I am Tesla. He was not formally qualified, probably, as either, and yet did a lot of work in both fields. Though he didn't, well, he said explicitly that he didn't understand all the physics of what was happening in some of his experiments. So probably he would have called himself an engineer rather than a physicist. But I think I'm Tesla would have been the answer.
He used to say that he was a discoverer. He used to say that was a discoverer because he thought that a discoverer was a different task than the one made by an inventor. He considered a high-level profession to be a discoverer than an inventor, and he usually say he used to say that he was a discoverer in front of Edison, that was an inventor. Another tale.
There is one story that Tesla said about Edison. He said, if Mr. Edison were asked to find a needle in a haystack, is that clear? Mm-hmm. Edison would take the haystack apart, one piece of straw at a time, and look at it, and eventually he would find the needle. If I were doing it, said Tesla, I would think about it for a minute and then do something rather more sensible than looking at every straw one by one. And that, he said, is the difference between me and Edison.
Bueno, con respecto a la disputa que tenían Edison y Tesla, hay también otra anécdota, pues un poco negra, que Edison decía que la corriente alterna era útil para la silla eléctrica, mientras que la corriente continua era de utilidad en todas las demás cosas.
Yes, Edison liked the idea that the alternating current should be used for the electric chair because it all supported the argument that alternating current is dangerous, my current is direct and safe. So he thought it was good publicity that the electric chair used alternating current. My system is safe. Have my direct current in your house.
Okay, I think it's time to close this conference. I want to thank you very much to Brian Bowers for his conference, for his very interesting conference. And I would like finally to invite all of you to come with us and know our exhibition outside at the entrance hall. Every day we have guide tours, including the weekends. We have also guided tours on weekends, so I invite all of you to come to know the exhibition. And I want to thank you, all of you, for coming, for attending this conference, and I hope to see you again in our second conference. Thank you very much.